All right. DRAM outline. So we will talk about the DRAM overview today, and then we'll talk about the basic cell operation, which is one transistor, one capacitor. And then we'll talk about the DRAM structure and layout, and then scaling challenges, and also the future trends. So once again, DRAM short for dynamic random access memory, and we understand those key features. Dynamic here means we need to do this periodic refresh. Otherwise, your data will be gone. And again, this is random access memory. So each bit can be independently accessed, read or write. And then DRAM is, again, the volatile memory. Once you remove the power supply, then you lose the data. So if you compare the DRAM and SRAM, so here SRAM is for cache, and DRAM is usually off chip, off the processor's chip as a standalone memory. And then the cell size, SRAM in the older generations, is about 150 F square. And then DRAM is like 6F square to 8F square. We'll talk about that later. So it's much smaller as a same technology node. And then SRAM is pretty fast. You can be like, below nanoseconds if it's a lower level cache. You can size up the transistor and make it pretty fast to be compatible with your 2 GHz, 3 GHz, 4 GHz clock. But DRAM is relatively slower, so you may need tens of nanoseconds to finish the entire row cycle, like 40 nanoseconds. And SRAM is non-destructive rate, but DRAM is kind of destructive. That means when you sense the data, you may change the data. But we have to prevent this from being happen. So we have some design tricks there called the write back. So SRAM cell leakage current, depending on the high VT or low VT transistor, but in general, it's larger than picoamp per cell. But the DRAM cell leakage should be very, very small. Otherwise, the retention will be very bad. So we need the transistor to drive the DRAM below like 1 femtoamp per cell. So there are some other differences, but I would say the DRAM fabrication is very optimized in a different manufacturing process. So that's why DRAM foundry, there's no DRAM foundry. DRAM fabrication is on separate facility than the logic foundry. Okay, logic foundry typically will not fabricate the DRAM technology because DRAM's fabrication needs very special consideration. So let's talk about the DRAM subsystem from the organization point of view. So here are some terminologies you want to be familiar with. So top down, we have the channel, DIMM, rank, chip, bank, and then maybe we have the mat in between, and then row and column. So what is that? Okay. So if you look at the DRAM subsystem, let's say if you open your desktop, right, or your server, then you will see this kind of board on your motherboard. This kind of like, printed circuit board on your motherboard of the system. So here, your processor may have different communication channels to a group of these kind of boards. So here, this is a channel, okay. But within the channel basically means you share the I/O, share the data bus. And then here you may have two of these cards inserted, right, to the motherboard. So each of this card is called DIMM, D-I-M-M, dual inline memory module. It's DIMM. So this one green card is one DIMM. And on the DIMM, you see many these black packages. Okay, those are DRAM chips packaged in this black plastic stuff. Right. Also, by the way, so here the DIN, you see that it has many pins here. There are like those metal pins inserted to your motherboard. Okay, there are many pins. But typically, let's say you may have 64 pins for the data I/O. Of course, you may have additional pins for like control and power and other functions. But in terms of data, you may have 64 pins for the data transfer. And then the DIMM, you may have two sides. You can have two sides to have those chips. So each side is called one rank. Okay. The DIMM, like a two side, you can have the chips packaged on two sides. Each side is called one rank. So here, in terms of the data flow, so let's say your front side and back side of this rank, each of that will give you 64 data at one time. Of course, you need to have a mux to select which side you're going to choose the data from. And then you send the 64-bit data to the data bus, as I said, the memory channel. And this memory channel, of course, may have additional like control signals to your rank. But in this case, each time you transfer 64-bit data. So if you break down the rank, let's say one side of the DIMM, you have those 8 chips. And actually each chip may only give you 8-bit data, and then you aggregate this data at the DIN level. So let's say each chip give you 8-bit data, and you have 8 chips, so you get 64-bit data. So here, if you break down the chip, you may have many banks. In this example, you have 8 banks. So here you may have 8 banks within the chip. So each chip, each bank will give you 8-bit data, and then you need a mux to select which bank you get the data from. Okay. And then if you break down a bank, you may see those memory cells in rows and columns, overline bit lengths, right? So here, this is one example. So DRAM bank could be very large in size. So for example, here it may have 16 kilo rows and also 16 kilo columns. So each bank give you, for example, here 16 kilo by 16 kilo, it give you 256 megabits. Okay. So here then, along the columns, you may group, let's say 8 bits, right, as 1 byte. So every time you activate this 8 bits, 1 byte data. So you will get the data to the row buffer, which is the sense amplifier at the edge of the array. And then every time you get this 1 byte, of course, you need the mux to select which byte you are going to transfer out, because each bank give you 8-bit out. So any questions here? Okay, because the bank is very large, so in practice, we may have further breakdown. So in one bank, there are many mats, basically smaller subarray size. So in this example here, this mat is like 1 unit of those rows and columns. And in this example, let's say the mat size here, if you look at this, is a real like a DRAM image, DRAM chip image. One mat is only this large, okay? And then here you may have 1K by 1K. This is still larger than the SRAM's typical subarray size. right? We talked about SRAM before, like 64 by 64, 128 by 128, at most 256 by 256. So here, this math is, for example, 1K by 1K, give you 1 megabit, and then one bank may have many of them, let's say 16 by 16. So one bank will give you this 256 megabits. Right? Actually, this kind of size is for not for the very advanced DRAM. I would say for older technology node, maybe 10 years ago, this kind of size. Okay, it's not for today's advanced, very advanced DRAM. But this gives you some sense how large the array size is. So any questions? Then very important, we'll talk about the DDR here. You may have heard of DDR. It's a protocol for the DRAM I/O interface. So it's short for double data rate. So what is that? Okay. So the DRAM, from the DRAM bank, internally, you may have the clock frequency like 200 megahertz. So here, this is different from the I/O's clock frequency. This is internal clock. And then you have I/O clock. I/O clock is going to burst this data out to the memory channel, right, through those pins. So here, in order for the DRAM to provide large bandwidth at the system level, then the I/O speed is overclocked. Okay. Internally, DRAM cannot really be very fast. Even for today's very advanced, this number does not change too much. Maybe from 200 megahertz for 300 megahertz, as I said. Okay. Even after like so many years, like 20, 30, 40 years, this number does not really change too much. There's a limitation. I will talk about that later, why this is no internal clock. So you cannot really do too much for the internal clock. But what you can do is to do this prefetch, okay? So for example, here you can get the data in parallel from, let's say, for 8-bit data, right? Every time you get 8-bit data. So because your subarray is so large, you can get many of those 8-bit data in parallel, right? You can activate more. So let's say one time you get 2 8-bit data in parallel. Then at the I/O, you are going to hear the double data rate, means you are going to send the data in both falling and rising edge of the clock. So it's like a double the data rate, because normally, you will only have the data internally, let's say, only fetch the data like your this latch, right? Only, let's say, rising edge, you get the data. But then here in the I/O, we are going to both send the data both in the rising and the falling edge to double the data rate. So effectively, you are going to increase the data rate to 400 megabps, 400 megabit per second. Right. The reason is that you prepare 2 data at one time. Even at this clock edge, internal clock edge, you have two 8 bits. So in the I/O, you are going to first burst 8-bit here, and then in the next rising edge, you transfer out the other 8 bits. Okay. To avoid confusion, let's say you get 1 bit, because per pin you're going to get 1 bit data. So let me just use 1 bit here. You're going to get 2-bit data here, and then you burst out 1 bit here, 1 bit here. So this is per pin. Okay. You need 8 pins for 8-bit data. Later you see like 64 pins, right? You get 64-bit data at one time. So per pin, let's say per pin, is 400 megabps. So then in the recent generations, right, you can play this trick. You can even further double the clock frequency at the I/O while keeping the internal clock the same. So if you double this, then you can prefetch 4 bits. Then you burst out those 4 bits. This is the same as 1 clock cycle internally, right? But at I/O, you got 4 bit out. You can do this effectively for 8, like prefetch 8 times, and then you get the DDR3 protocol. So the I/O now is 800 megahertz. Then you get 1.6 gigabps per pin. So this is DDR3, and today is already DDR5. Okay, so you can double, keep doubling. Okay. So essentially, what you are doing here is to do this parallel to serial change. So you are going to get 8 bits in parallel, for example, and then you are going to burst those 8 bits out with a faster clock as the I/O, right? So it's a parallel to serial process. So this interface is serialized or deserialized between this core and interface. So I skip those text here, but essentially what we are doing is like this. You prefetch more bits, and then you burst out. So here are some numbers you can take a look. So for example, 200 megahertz, that means 5 nanosecond clock internally. And then you have this CSL pulse to get the data. I will talk about that later. So basically, this is the internal clock to get the data. Okay. So the system level bandwidth could be like 12 gigabyte per second. So if you are on a 64-bit data bus, so each pin you need 1.6 giga or 1,600 Mbps per pin, because you need to divide it by 64 pins here for the system. And each pin, right, if you use DDR3, you will get this data rate. So any questions here? So essentially, this DDR is playing this serialization from the parallel prefetched data at the I/O and then burst it out. Okay, and I think time is up, so we'll stop today here.